Okay, the first law of thermodynamics is basically the idea that any one system's internal energy is equal to energy input minus energy output. It's pretty cut and dry, but there are, a couple of things we can take out of this. This is usually written mathematically as delta U equals Q minus W. So one of the things we can kind of extract from this, right, is that energetic states are relative. So for instance, say you have three systems connected to each other. Okay, system 1 is connected to system 2, and system 2 is connected to system 3. And let's take our metric of thermodynamic equilibrium to temperature. So we've got 2000 degrees Kelvin, 2000 degrees Kelvin, and 2000 degrees Kelvin. Well, because they're all 2000 degrees Kelvin, there's no flow, or there's no flow of thermal energy from one system to another. They're at total thermal equilibrium. So even though all three of them are at 2000 degrees Kelvin, because this particular law, is basically telling us that energetic, a system's energetic state is really relative to its surrounding, connected state or systems. Its energetic value really is zero because there's no flow, there's no input or output happening. So it has, it's in total energetic stasis. There's no flow happening. Okay, so it's relative. And to make this point, if you had same three systems, so one's 2000 degrees, one's 500 degrees, and one's 5 degrees, well, the energetic flow is going to obviously come from, the thermal flow is going to come from the system that's 2000 degrees, and it's going to flow fairly quickly and heavily into the system that is at 500. And the system that's sitting at 500 is going to flow quickly and heavily into the system that is, 50? Okay. So there's quite a bit of input and output, for this middle system, which means it's got a lot going on. It's pumping stuff out, it's taking stuff in. So, yeah. If we move on to the second law of thermodynamics, that is the well-known law of entropy. One thing we need to know about entropy is that entropy always increases. That means that systemic disorder is always increasing or multiplying. Or not multiplying, I'm sorry. Disorder is always happening. Things are moving and tending towards disorder. And that is what we were talking about when we were talking about an increase in entropy. Now, one of the sort of indications of this guy, or one of the lessons we can pull out of this, is that entropy does not ever flow backwards, which means that heat, any kind of, okay, if I have, let's go back to the three states or the three systems, right? I have the 2000 Kelvin state or system, and I have the 500 Kelvin system, right? Energy from the 500 Kelvin system is not going to pour into the 2000 Kelvin system. It simply is not something that happens. So, yeah, entropy always increases, and this sort of increase in entropy and in chaos never goes in the reverse order. It's always going in one direction. Okay, third law of thermodynamics is basically states that as you approach 0 degrees Kelvin, And this is, when we say approach 0 degrees Kelvin, we're talking about it in the same sort of fashion that we're talking about a limit. You're never actually going to get to 0 degrees Kelvin for several reasons, but theoretically, okay, if you were to get to 0 degrees Kelvin, you would, your material, your particles would have no vibration, they would have no spin, they would have no movement, they would be completely and totally frozen. Okay, zeroth law of thermodynamics. Now this is easily equated to the transitive property of equality. The transitive property of equality states that if A equals C and B equals C, then A is equal to B, okay? That is fundamental mathematics right there, right? This also is applicable to thermal equilibrium. So, and that is essentially the 0th law of thermodynamics. That is what it is saying. That is talking about the fact that if system A at whatever thermal equilibrium is equal to system C thermal equilibrium, or thermal energy level, right? Thermal state, and B is also equal to C, then system A is also equal to system B thermally, when we're talking about thermal equilibrium.